So welcome you back to this module. So what we were doing last time was we derived expressions for orders of various expressions of functions of x bar. So in particular, the most general result which we derived was if my Cn is a sequence of the type an plus a by n plus O of n square, and if I have to find expected value of h of Cn x bar, of course, the assumption is that for some k greater than or equal to 3, h has kth derivative which is bounded. So h of Cn x bar in that case is h of mu plus a mu upon n h prime mu plus sigma square by 2n h double prime mu plus big O 1 upon n square. And then we also saw that variance of h of Cn x bar is same as sigma square by n h double prime mu plus, sigma square by n h prime mu whole square plus little o 1 upon n square. So this we saw last time. So of course, if Cn you can take as sequence as 1, that means a is 0, I can get the expression for h of x bar and variance of h of x bar. So let's try to do one example based on it and see how this result is going to be useful. So let us do this example. Suppose x1, x2, xn are IID, normal theta 1, where theta is a parameter which can take any real value. And my estimand is g theta, which is phi of u naught minus theta for a given constant u naught. So u naught is given to you. So this is like a quantile. This will be nothing but quantile because this is same as probability that theta x1 is less than or equal to u. That is what you are interested in is. So if you see what is the UMVE? UMVE from your last class, let me not do it, I'll just give you a hint. Delta nx is nothing but, yes, phi of root n upon n minus 1 and u naught minus x bar. First, let us try to see. So what I try to do is, if I can write down this as h of Cn of x bar, I'm done. Then I already have a ready-made expressions, and I can do that. Of course, I'll have to see whether my phi satisfies the assumptions of last theorem. That means for some k greater than or equal to 3, phi should have a bounded derivative, bounded kth derivative. So first, let us try to see what is root n upon n minus 1. So this is nothing but 1 minus 1 by n to power minus half. All right? Which is nothing but 1 plus 1 by 2n plus big O 1 by n square. So it is the Cn of the last type where a is 1 upon 2, because it is 1 plus 1 by 2n plus big O 1 upon n square. So what I do is delta nx, I write down as h of Cn x bar, which is nothing but, and where what is h? Where h of x is, Cn has come over here, so u naught minus x, phi of u naught minus x. So the only thing I need to say is for some k greater than or equal to 3, phi should have, h should have a derivative, kth derivative which is bounded. So let us try to do that one by one. So for h prime x is nothing but phi of u naught minus x, all right, where phi is the PDF of normal 0, 1. Capital phi is a distribution function of a normal 0, 1. Okay, let us try to see what is h double prime x. Is nothing but phi prime of u minus x, and that becomes minus minus becomes plus, so it is phi prime of u minus x, u naught minus x. And you know that if phi is the PDF of normal 0, 1, then phi prime t is same as minus t times phi t, because 1 upon root 2 pi e to power minus t square by 2. When I take the derivative, e to power minus t square by 2 remains as it is, then the derivative of minus t square by 2 gives me minus t. So this is nothing but minus of u naught minus x phi of u naught minus x, all right. I have to see the third or fourth derivative. I go up to third or fourth derivative. So let us see h3x. The third derivative, I first differentiate this with respect to x. That makes it phi of u naught minus x. Then minus u naught minus x, phi prime of u naught minus x, but derivative of x with this will give you phi prime of u naught minus x, which is nothing but phi of u naught minus x minus phi prime of u naught minus x is same as again minus phi of u naught minus x, so minus u naught minus x whole cube phi of u naught minus x. In fact, the third derivative you can see of h3, as x goes to infinity, this goes to 0. So the third derivative is bounded because h3x is going to 0 as x goes to infinity. So asymptotically it is bounded. So that means in general it is bounded. But you can see that h4x, so this is bounded, right? Why? Because this goes to 0 as x goes to minus infinity to infinity. So on the tails it is bounded when x explodes, and phi being a continuous function on a closed and bounded interval, it will be bounded. So it is bounded. So I can use this expression. So expected value of delta of x is nothing but expected value of h of c n x bar, which from here is nothing but h mu plus a mu upon n h prime mu plus sigma square by 2n h double prime mu plus big O 1 upon n square. And how much is that? My h of x is nothing but phi of u naught minus x. So I am talking about h of mu. So that means phi of u naught minus mu. Sorry, everywhere in place of mu I have to take theta, right? Because x1, x2, xn is IID normal theta 1. So this is nothing but phi of u naught minus theta. That gives me h of mu. Basically it would be h of theta. Everywhere mu is basically theta because x1, x2, xn are IID with mean theta. All right, phi of u naught minus theta plus a theta by n. What is the h prime of theta? Minus phi of u naught minus theta. so minus phi of u naught minus theta, plus sigma square by 2n h double prime theta. H double prime theta you have calculated from here, so which is same as minus of u naught minus theta phi of u naught minus theta plus little o 1 upon n square. And what is A? A in this case is 1 by 2 in our case, because Cn is 1 plus 1 by 2n, so it is 1 by 2n. So you can see that minus theta by n phi u naught minus theta, and here plus, yeah, so this is what you get. What is the sigma square in our case? x1, x2, xn, IID, normal, theta 1. So sigma square is also 1. So this you can simplify. What is the variance of h of Cn x bar? Variance of delta nx? Which is same as variance of h of Cn of x bar, which you have seen is sigma square by n h prime mu whole square. So sigma square by n, h prime mu is phi of u naught minus theta, so phi square of u naught minus theta plus big L O 1 by n square. So you could get expression of this. So very simple, just once we had a ready-made formula from the last theorem, we could do that. So now let me just quickly go through the expressions of expect loop x bar minus mu whole cube as well as expect loop x bar minus mu to power whole 4. We have, although we have done it for general expect loop x bar minus mu to power 2k and 2k minus 1. To get a better insight, I can just show you how does it work for cube and x bar minus mu to power 4. So let us try to see. So x1, x2 are IID. Expected value of x1 is mu. Variance of x1 is sigma square. Expected value of x1 minus mu whole cube is mu3. Expected value of x1 minus mu whole 4 is mu4. I need to find out, of course, expected value of x bar you know is mu. Expected value of x bar minus mu whole cube, sorry, whole square is nothing but variance of x bar that you already know from your earlier courses is sigma square by n. I would like to get an expression of expect loop x bar minus mu whole cube. Now note that this can always be written as 1 upon n cube into expected value of summation I is equal to 1 to n xi minus mu whole cube. So let's try to see how can I write down expect loop of summation I is equal to 1 to n xi minus mu whole cube. This is nothing but summation I is equal to 1 to n xi minus mu. Summation j is equal to 1 to n xj minus mu. Summation k is equal to 1 to n xk minus mu. So 3 product. Now when I am considering this product, in each term in this product, each of these sum will contribute once. So one term will come from each of these sums. So let's look at what are the different possibilities. It is the same index coming from each of them. That means xi minus mu comes from here, xi minus mu comes from here, xi minus mu comes from each of them. All such factors will give me xi minus mu cube. So for example, I'll get x1 minus mu whole cube, x2 minus mu whole cube, and xn minus mu whole cube. So one is, this is same as summation I is equal to 1 to n xi minus mu whole cube. What is the second one? Second one is from two of them I get the same. So let us say xi minus mu whole cube I get from 2. Those two could be 1 and 2, 1 and 3, 3 and 2. Each of them xi minus mu is coming, and from the rest one, let us say another one xj is coming. So this would be 3 times summation I naught equal to j xi minus mu whole square into xj minus mu. So two of them comes same and one is different. Third is, from all of them I get a different. So that means here I get xi minus mu, xj minus mu, and xk minus mu. All of them are different. So I not equal to j not equal to k, xi minus mu, xj minus mu, xk minus mu. Now note that if xi minus mu is coming from here, xj minus mu is coming from here, xk minus mu coming from here, any permutations would also do. So how many such cases would be there? Factorial 3, which would be 6 such cases, which is equivalent to saying that first I choose one position for I is coming from one, from one of the 3's, so 3 choose 1. Now I has been chosen, I choose the position for j, so remaining 2 are left. From them I get 2 choose 1, so 3 choose 1 into 2 choose 1 is 6. And once I and j are determined, position of k is already determined. Right, so now I am done. So expected value of summation I is equal to 1 to n xi minus mu whole cube will be how much? Each of them is IID. So for each of them this is mu 3. So it is n times mu 3 plus. Now this term is going to be 0 because of independent this would be x of xi minus mu whole square into x of xj minus mu, but that is 0. Similarly here, because of independence of I, j and k, it would be x of xi minus mu, x of xj minus mu, x of xk minus mu. Each of them would be 0. So this is 0. So what do you get? So expected value of x bar minus mu whole cube turns out to be mu 3 upon n square. Now by the same logic, if one has to look at x of x bar minus mu to power 4, it will be 1 upon n to power 4 expected value of summation I is equal to 1 to n xi minus mu whole power 4. So I need to calculate what is this. So you can do exactly the same way. If summation I is equal to 1 to n xi minus mu whole 4 comes, I write down as this as a product of 4 different terms. Summation I is equal to 1 to n xi minus mu. Summation j is equal to 1 to n xj minus mu. Summation k is equal to 1 to n xk minus mu. And summation L is equal to 1 to n xl minus mu. So again, same kind of a scenario that each of these sum will contribute once in a product, one term in the product. So one possibility is all of them give the same, which is nothing but xi minus mu, so that is same as summation I is equal to 1 to n xi minus mu whole 4. The second is 3 of them give the same. So for example, x1 minus mu cube is coming from 3 of them. And remaining one, something else is coming, different from 1. So 3 of them can come from 1, 2, 3, 1, 2, 4, 2. So 4 choose 3 positions, right? So 3 of them are same. And then remaining position can go to remaining 1. So that is same as summation I not equal to j xi minus mu whole cube into xj minus mu. Now, I get the same only from 2 of them. That I can be chosen in 4 choose 2 ways. Then remaining 2 are left. The possibilities remaining 2 also I get the same. So which would be 4 choose 2, only remaining 2 same, so they are already determined. So xi minus mu whole square into xj minus mu whole square. The other possibilities is I get 2 same xi minus mu whole square, and remaining 2 are different one, j and k. So that means summation I not equal to j not equal to k. So 4 choose 2. So let me write down. Then jth one, remaining 2 are left, so I can get one of them. So 2 choose 1. 2 are remaining. I choose the position for j in one way, and then k is remaining, so it gets the whatever is remaining. So summation I not equal to j not equal to k. xi minus mu square, xj minus mu, xk minus mu. And then, so these are 2, and then that's all, because 1 and that is covered over here. So what do you get from here? So expected value of x bar minus mu to power 4 turns out to be 1 upon n to power 4. This is n mu 4, right? N mu 4 plus. This will not contribute because of independence. This would be x proof xi minus mu whole cube into x proof xj minus mu, which would be 0. Then it will be this quantity, x proof xi minus mu whole square. Because of independence, it would be x proof xi minus mu whole square, x proof xj minus mu whole square. Each of them gives me the sigma square. So it is sigma to power 4 into n minus 1. And 4 choose 2 is nothing but 6. So 6n into n minus 1, sigma to power 4. And similarly, the last term would be 0. So this is what you get, and which is nothing but mu 4 upon n cube plus 6n into n minus 1 sigma to 4 by n to the power 4, which is big O 1 upon n square. So let me just stop over here. So what we were doing is that we saw that if you have to compare estimators asymptotically, one way to compare estimators asymptotically is you compare their limiting risks, and which led to the concept of a limiting risk efficiency. And the second method is because in many situations risk may not exist, the movements may not exist. And it may happen that the region where risk does not exist becomes an empty set as n goes to infinity. So it makes sense that we compare their asymptotic distribution and see what is the asymptotic variance of such a distribution. So the second approach to compare estimators asymptotically is through their asymptotic distribution, and then I consider what are the variances in the asymptotic distribution. So that we'll do next time, and that's all for this module. Thank you very much.